Hi everybody, we are in week 3 right now and we're still dealing with the second chapter of this class, which is chapter 22 of the book. And we're still dealing with Gauss's law. As I was saying before we started the recording, Gauss's law is really, it looks ugly, it looks complicated, it looks hard, but its utility is actually in the fact that it takes advantage of the symmetry and makes hard problems simpler. As I was saying in the beginning, as I was said actually last time, Mr. Newton, because he did not have the advantage of calculus at that time, it was not invented, it took him 4 years basically to publish his work. He already had an interpretation for Mr. Kepler's laws, and it took him that long really to publish his work because he was afraid of a criticism that people would direct to him in that the apple, why in the world you just argued that it's the distance between the two objects, m1 times m2 divided by the distance squared. And in here, we clearly see the distance between the apple and the Earth is about 1 meter or 2 meters. So why did you plug in the radius of the Earth instead and assume that the entire Earth is somehow in the center of the entire mass is in its center? We can understand basically how you treat the distance between the Earth to the moon when you're talking about the moon, because that distance is about 380,000 kilometers, whereas the radius of the Earth is about 3,600 kilometers. So 380,000 versus 30,600 is negligible. So it doesn't matter where you take that the mass of the Earth, whether it's in center or what at the surface. But for the case of the apple, clearly that's going to be a major problem. So he couldn't make the case for that, and he knew it has to be so that the Earth is actually at its center, all of its mass is at its center, and the apple is roughly 3,600 kilometers from its center, and that gave him the beautiful mechanics that he went for to explain the motion of all of the planets, not just that of the moon and the apple. So it took him that long really to make the case for it so that he will face his critics with open arm, because then he is empowered with the knowledge of why that is, and for that he had to invent calculus. And that is similar to the problem that we did actually in a sense last time using Gauss's law. Let me share with you the screen of what we did last time. Share. So of course we did it in the case of magnetism. And why is my cursor not moving? For some reason, this is stuck. Okay, sometimes if I refresh in and out, it works. Okay, it does. Okay. Excuse me. So basically, what we did then, we took a charge rho, that is, charge q, that is sprinkled throughout the entire sphere. And this sphere, and it's a key concept in here, better be insulating, okay? We'll see why that is very shortly when we define what a conductor is. Once we know what a conductor is, this sphere must be insulating if we expect the charges to be sprinkled uniformly throughout it. If we expect these charges, let's say, for example, I have a bunch of charges in here that is sprinkled uniformly. So I have let's take it positive charges everywhere, and they are everywhere with the charge distribution rho per unit volume. That means if I take a dV volume in this case, I have a rho charge in that volume, meaning rho has the units of Q over Coulomb over meter cubed, as is clearly stated in here. We will see conductors have a different behavior. So I'm going to assume that this is an insulator from now on. If it's a conductor, this behavior is not going to, for a conductor, it's going to spread throughout the thin surface only. It's not going to penetrate the charges no matter where you try to put them, okay? They will only stay on the edge. They don't go inside, okay? So basically, we argued the electric field in there, and this is actually a good justification. So if I look for the electric field outside, when R is greater than R, this is how it behaves. It behaves like Q over 4 pi epsilon naught divided by the distance squared. This is similar to a point charge. Remember, for a point charge that has no physical size, basically, that's what a point charge is, E was equal to Q over 4 pi epsilon naught R squared, where Q is the charge itself of the point charge. Q, in this case, big Q, is the charge on the sphere itself, everything included. The two expressions, they look identical, okay? So what this says then is for a solid sphere that is an insulator, it looks like it's a point charge situated in its center, because this distance, as I'm measuring it, is from its center, not from the edge, not from the surface, not this distance. It's not this one. So it's the whole distance from the center to there, and the two expressions look identical if we are outside of the sphere. If we are inside the sphere, though, it's a different behavior. It's this expression that is linear in E, okay? So if we were to restore the direction of the current for R less than big R, the electric field, we found it to be Q divided by 4 pi epsilon naught R over R cubed. Q divided by 4 pi epsilon naught R over R cubed. I'm going to say this one is actually the direction of R, because this is radial. It's in the same direction as R, because we argued by symmetry that it's pointing radially away. So if I want to put the vectors back, we're in business. Now, I also could express it in terms of rho. Remember, rho is Q over V, or 3Q over 4 pi R cubed. So this R cubed and 4 pi, all of them will be consumed, but I will pick up a 3 in here in the denominator coming from this expression. So it's going to be, so basically 3 in the numerator divided by, let me express, I think we found it in terms of, so this is how it looks like again. If we were to simplify here, we were to simplify in there. So this, then E will simply be equal to rho R divided by 3, epsilon naught. So this is in terms of rho. Remember, we sub the value of rho in there, okay? So in terms of rho, it's the same thing. So E is equal to rho divided by 3 epsilon naught times R, okay? This is identical to this expression, by the way. This is the same thing, because all I did was sub the value, and it's both of them are radial. The main thing is that it depends on the distance, how far you are inside. For the outside, it drops like 1 over distance squared. For the outside, when R is greater than R, it's equal to, again, I'm going to restore the charge in the sign in here for the vector, Q over 4 pi epsilon naught times R squared times R hat, because I'm putting the vector back. Sometimes, so it's radial still, and this is outside, okay? Sometimes the vector R hat is equal to as the ratio of the vector divided by its length. It's the same thing. It's the same thing to say a unit vector, because R vector is its magnitude times its direction, and this is the direction, the radial direction, okay? So sometimes this very same expression, even for the point particle, you might find it written, and it's true also for Newton's law, because there is a parallel with this one in Newton's law, is written as Q as a vector R, not R hat, divided by 4 pi epsilon squared R cubed. And you might think that, hold on, this depends like 1 over distance cubed, but it's not, because there is a distance also in the numerator, so it's still 1 over distance squared. This is just a matter of writing, that's all. But the point being in here, this is the electric field outside for a solid sphere. That is insulator, as I was making earlier the case for that. I didn't actually make the argument yet, but at least I'm insisting on the fact that it has to be sphere, because if it's not, I'm telling you up front that it's not going to work. At least inside, the electric field is not correct, okay? Inside, this is not going to be correct for the sphere. This may still work for the sphere if it's a conductor. Okay, so we're going to talk about that shortly. The reason why I'm doing this expression right now, especially this one, is because we will need it for problem 53. Initially, I was tempted to do it, but now I think I'm going to do problem 53 because I think of its importance. When I was taking this class a long time ago, when I was first exposed to this idea, I thought this is the cleverest thing ever. It's cleverer than anything else that I have seen in my life. So I thought I need to share with you problem 53 because it's of its beauty really, and how to solve a lot of problems that involve this kind of problems in engineering and physics like that. So without really doing a lot of effort. So again, we will need this result. Actually, as a matter of fact, we will need this result for problem 53. Okay. Then we also did another thing, didn't we? We did the long wire. This is what the case was. Basically, the long wire also had we used the symmetry in that case, the cylindrical symmetry, and we argued for the electric field has to be pointing outside, basically in the radial direction with respect to the lateral surface, and also its magnitude is the same as long as I stay the same distance y from the wire. Okay. So if I move further away, expect the electric field to be less because I am further away from the wire. As a matter of fact, if I am at infinity, I expect no effects whatsoever of this wire on infinity, so there will be no electric field away from it. If I get closer from the wire, I expect the effect to be present, and that's why I thought at the distance y from it, it has to be the same by symmetry, because if you argue that it's one way is more than the other, all I have to do is move the infinite wire one way or the other. And you wouldn't tell because it's an infinite wire, so it's still that nothing has changed as far as the distribution of charges in this case. So why in the world then the value that was in here shifted? I mean, at least for you, you think that it has changed without any cause for it to change. Because of this cylindrical symmetry, therefore, it must be the same. In other words, the electric field in here must be the electric field in here, must be the electric field everywhere distance y from the wire. That's basically the argument of symmetry. That makes the case that E is constant throughout the entire lateral surface, and basically all you have to do is just multiply E by the surface, and the surface for the lateral for a cylinder, the lateral surface that is, it width times height, and the width times length. And the width, I took an arbitrary value L in there, so we expected the answer not to depend on it because it would have been a disaster if it depends on it. And the width in this case is happen to be 2 pi times y, which is the perimeter of this cylinder after we cut through it and open it. So basically, this is the lateral surface. The basis would not contribute because of the fact that we just argued that the electric field must be pointing away again, to retain this symmetry, because if you argue one direction, I can rotate the spin the entire wire while you're not paying attention, and tell you, did anything change? And you tell me the wire is still the same, but for some reason the electric field now is pointing in the wrong direction than what I thought it was. So to retain that symmetry for this transformation, then the electric field must be pointing upward in such a way, if we rotate it, you wouldn't think that the wire has something happened to it. It's still the same wire. It looks the same wire with the same distribution, and it's an infinite and all of that. And the electric field will also retain its direction. So again, that is the argument of symmetry for the electric field pointing away, and then the area is actually pointing at 90 degrees away from it. So the dot product will give me 0. So the two bases will contribute nothing in this case because of the property of the dot product, and the contribution is coming from the lateral surface. The troubling thing in here is that you have that L, which is not part of the real problem. Why it is? The distance is, and the electric field is what we want to find using Gauss's law. But then if we equate it to the charge enclosed divided by epsilon naught, and we have lambda charge per unit length, and it took length L enclosed by this surface, so that means I have lambda times L charge, and all is well because now the L cancels from both sides. Because it's a fictitious thing, it's not a real thing, which came up with the prescription on how to handle problems with using Gauss's law. So you need a symmetry for it, otherwise you have a problem. Problem 53 is not symmetrical, okay? The problem that I promise we will do does not have really spherical symmetry, it doesn't have none of that. Yet, using Gauss's law, we're going to be able to solve it, okay? So this is basically, in a nutshell, what we did last time. Since I made a big fuss over the conductors versus non-conductors or insulators, we're going to get into that. So what is a conductor? By the way, when we meet on Wednesday, we're going to finish this chapter because we're not going to be able to finish it today, including the problems and all of the things that we're discussing in here. So conductor by definition is they're all metals basically, like iron and copper and silver and gold and all of these things. They have their electrons, their electronic structure in such a way their electrons are communal. They are not really they don't belong to a specific atom. So if you have atoms in here anchored in place, and they have electrons in here, these electrons, they don't belong to this specific atom, okay? They're free to move whenever there is a chance for them to move, okay? So if you apply an electric field, let's say, for example, in this direction, of course, the electrons will move in the opposite direction, okay? So this electron will move this way because it's under EE, okay? And this electron will move there, and this electron will move there at will. There is no reason for them. They're not strongly anchored to their atoms. And once this one moves, now this atom now becomes positively charged because it lost an electron. This electron will hop in here to replace it. Okay, so that this charge in here stays neutral, stays zero. And this, since this electron hopped in there, this one now seems to be deficient of an electron. But don't worry, this electron will come in here because it doesn't belong to really to this one. It belongs to the community of atoms. So in this case, this is neutralized. Okay, and so is this one also because of the fact that, and so on and so forth. So at any given point inside the conductor, the atoms are actually still neutral because all they have to do is take from their next neighbor. Because not take, but they don't really do anything, the atoms. The electric field is the one that is making these charges move. As long as you have an electric field in this way, the charges are hopping one way or the other to basically because they're at will. They can move with that electric field, and that's the end of it. So that's basically how a conductor is. Versus an insulator has a different picture. Insulator, like for example, wood and air. If air is not an insulator, we'll have a problem before us. So in this case, you have an atom and it has its electrons. They are all in here. Even the outer ones, they are all anchored to it. So the fact that you apply an electric field this way wouldn't do anything because none of these charges are allowed to basically to leave it, at least for weak electric fields. When the electric field is so strong, then even here, you're going to see charges move, okay? Does anyone know a phenomenon that breaks the air and causes the charges in the air to all of a sudden start moving? Do you know what that phenomenon is called?
That laning?
Yep, that's it. That's actually electric discharge. It can happen even inside an insulator if the electric field, so now you have the clouds that are rubbing, basically building charges on themselves. So there is tremendous amount of charge, at least in the lower clouds, and the upper clouds also, they're building charges too, opposite to it, because charges are moving, and now there is a huge charge buildup. So there is a lightning actually between the lower end and the upper end. If you flew on a plane, you will see that. But also between the ground and the earth, now there is a buildup of charges, and that is going to cause an electric field so strong at some point, if it reaches a breakage point, it's going to go through the air. So even through an insulator, you could have charges moving, but you really have to do it via strong. Where is my share? Did I lose my share? Show all windows, here it is. You could do it, but as long as the electric field is strong enough to do it, okay? But normal electric fields that are used inside daily applications, like for example, for a current, they wouldn't do that. They wouldn't cause that, okay? But you could, theoretically, you could also do it in an insulator. So because the atoms in here, the electrons, they are not communal, but rather belong to their specific atoms. Electrons strongly bound to their atoms. That is the difference between the two. Okay, those are the two kinds of materials. We're going to group them. I know that there are semiconductors and superconductors. We'll talk about them down the road when we meet them. But at this point, these are the two main classifications of materials that we're going to see. So materials are either conductors or insulators. Okay. Conductors such as metals, insulators such as wood, for example, or air. Okay, so those are the two classifications. Look at let's take the metal now, the case of the metal, and wonder where in the world the electric field is. So I'm going to take a bulk in here, it doesn't matter. So this is a blob of a conductor. This is not a 2D shape, by the way. I'm trying to make a 3D shape, okay? And I want to find the electric field. Actually, I take a charge Q, I'm sorry, and I sprinkle it throughout the entire conductor. So this is a conductor now. So here is a conductor that you try to sprinkle the charges in it. Because of the fact that this charges in here, they cannot exist inside. Let me tell you why the charges cannot exist inside. And they have to, this charge that I'm sprinkling must be distributed. It doesn't mean that it's negative, it could be positive. I'm just showing the location for this charge, okay? So these charges must be spread throughout the surface only, they cannot go inside. Because if they're inside in here, let's say, for example, there is a charge that somehow has migrated inside, okay, negative charge or positive charge in here. That charge will create its electric field, okay? And that electric field will cause the other charges now to move. So there is a charge in here, a negative charge, an electron will come in here and cancel that one. So if you have one electron, if you have 10 of them, 10 electrons will come in here and basically start to move until they cancel this one, okay? And this charge now, of course, you're saying in here, okay, it was a positive. I put 10 Coulomb in here, and I have 10 electrons, I'm sorry, positive 10 electron Coulomb, 10 times 1.6 times to the negative, basically 10 electron values of an electric field that is positive. So 10 electrons will move to cancel it. Now you say, okay, that has shifted here. Okay, yeah, you're right. Okay, it has shifted there. But then the next 10 in here will come and fill up the gap until they cancel that charge. Okay, and they will do so until where could they grab from? The last point is the edges. Okay, so the last place that they can grab from is the edges to cancel every single charge inside. So there cannot be charges inside an insulator. Why? Because if they do, others will move to cancel them. Now, if you say, for example, no, I actually put 10 10 electrons basically. So it's 10 negative charges. Well, this electrons in here, because of the fact that they created their own electric field now, they will repel these electrons and they will keep on moving because they want to neutralize again, because they don't belong to anybody, okay? And all of the electrons inside the metal do not belong to a single atom. So they will move around until they find themselves actually at the edge. At that point, they cannot leave the metal. You need something called the work function. I know some of you are sitting in my physics 4C and know about that, in order for you to have the electrons actually extracted from the metal, okay? So, and as long as you don't have that, which is a big energy basically for this particular example, to have it to exceed that, and you can actually do that too, if you have seen those spheres, at least in the experiments that the Russian guy who came in, I forgot his name anyway for right now. Basically, the lightning, the discharge also. If you experimented with the man, I'm losing my. Let me check the book if this chapter has it. The picture of the girl in the front of the chapter 22. Okay, I'll try Tesla coil. Yeah, Tesla. Very good. Okay, but I'm looking at the word also. We used to do that a long time ago. We have them. You see, if the first picture of the girl on the book in here, she puts her hand, and all of a sudden the charges are actually spread throughout her hair. When you're talking too much, sometimes you start forgetting what you're supposed to know from basics. Anyway, so the charge inside the conductor does not stay inside the conductor, but rather goes throughout its surface. So you ask, what is the electric field then needs to be, okay? So the electric field inside must be zero, because if I take that metal and take any closed surface in here, okay, take any closed surface, it doesn't matter. This is a closed surface, not, by the way, it's three-dimensional shape. And since the charges, there is no charge in here, so the charge enclosed is 0, enclosed. So if I apply Gauss's law on this surface, the integral over this closed surface, any closed surface inside the conductor of EDA must be 0, because there are no charges enclosed. You cannot enclose in charges because it's equal to charge enclosed divided by epsilon naught. So this is 0. Since this surface is arbitrary surface, the only way for this integral to be 0 if the integrand actually is 0, if E is 0. So there is no electric field inside a conductor. That's interesting, because I can take a conductor now and apply to it an external electric field and see what's going on. So if you have a sphere now, I mean a shape, it doesn't matter if it's a sphere or anything, and you apply an external electric field to it, that electric field can go around it, but it's not going to go inside of it, because if it goes inside of it, the charges in here inside of it, what happened to them? They will move around in such a way to compensate for this electric field. So if this is an electron, electron will move in here. So there will be a pile-up of charges in here and in here. So they will leave depleted charges on this side, and they will end up with positive charges on this side. And the same thing in here. So they will leave their ions, and they will do it in here in such a way that inside there is no electric field. You ask how many are they going to move? They will be moving just enough to cancel the external electric field. So if you apply, for example, 10 Newton per Coulomb electric field inside, just enough electrons will move to compensate for it, so that they will have their own electric field of 10, so that the total is 0, in such a way that EDA over any closed surface inside the metal is still 0. Because if all of a sudden you have an E now, the charges will move until they will cancel that. They will cancel the applied electric field, the external field. So this is the behavior of metals. Okay, this is unique to metals. Conductors, no. You sprinkle charge like what I would. I mean, the conductor, the insulators, no. You sprinkle charge and they're going to stay there, because there is no. They're basically, if you remove an electron from an atom, it cannot extract one from its neighbor, because that belongs to its neighbor and you cannot take it from it. It stays there. And if you add an electron to it, it cannot do anything with it. It cannot push it to the other neighbors. Basically, it's going to be stuck in that position again, because of the fact that in an insulator, it's not easy to move charges. Whereas in a conductor, it's much, much easier. Actually, the electrons, they don't belong to anybody, and they will move at will once they see an external field or there is an imbalance of charges to balance one another. I hope that this distinction makes sense to you guys. Yes or no? Between these two kinds of materials. Okay. Thank you very much, James. Okay, listen to me. This is the question of the day, okay, for today. I know we have another one that is coming shortly, and the other one you probably guessed what it is, and that is to check my numbers and solve the problem, make sure that you finish the problems that we start working on. So the first question is basically compare and contrast between a conductor and an insulator, and the comparison falls into two basically things. Inside the conductor, the electrons belong to the community of atoms. They don't belong to specific atoms. Whereas inside an insulator, they belong, each atom retains its electrons, basically. If it has an excess, it cannot get rid of it. If it has deficiency, it cannot borrow. Okay, that's one thing. The charges inside a conductor, of course, they're going to be neutralized, and it's going to stay 0 no matter what. No matter, even if you sprinkle charges, they will stay to the surface, but they cannot go inside the material. So the inside charges are always 0. And that is, as a conclusion to that, inside the conductor, the electric field is 0. And that's by Gauss's law. You see the two things and how they are comparing to one another? And that's what really can take advantage of the situation for conductors to do electricity, because if we apply an electric field and sustain it on both ends, now charges, they can start moving as long as we're pushing them aside on the other side. So if a charge moves from here, we better supply it in here on this end so that when it comes out from the other end, we push it in. And that's exactly the role of the battery. All the battery does is make sure if charges started to leave from the other end, it grabs them and put them to the other end and continue the circuit. So that's basically how currents work, okay? So that's exactly the idea why currents work with conductors, and they don't work actually with insulators, because you apply an electric field on an insulator, nothing happens. Charges will not move. So they stay there where they're stuck, okay? So that's basically, in a nutshell, the difference between the two, and why one of them is called the conductor, because it conducts electricity, and the other one is called actually an insulator, because it doesn't conduct. It actually isolates the electricity current and does not go through. Does it make sense? This comparison? Okay, very good. So let me look at the electric field at the surface of once we do that later on, we're going to, I can't see the chat, you guys. Okay, again, this screen seems to be stuck now. It's moving now. Okay. Let's do one more shape of interest for the next two chapters, actually for the next course completely, and that is an infinite plane, the electric field of an infinite plane. Okay, I'm going to go back to an insulator in here. Doesn't matter, since it's an infinite plane, it's going to be super thin. So even if it's a conductor, the charges are going to be on its surface. If it's an insulator, they're going to be in surface. So I'm going to take an infinite plane. Okay, big area A. A is infinite. Huge area, okay? Compare it to the distance where I want to find the electric field. So I'm in here at a distance y, okay? And I want to find where the electric field needs to be. I'm going to assume now that this charge is used, we use the letter sigma in this case, Q over A. So you take a charge Q and you sprinkle it over a huge plane, okay? And you would want to find the electric field produced by these charges that are on an infinite plane, okay? Obviously, we expect at least the following. If we are closer from the plane, the electric field should be strong. If we are away from it, let's say, for example, we are on the other side of the universe, this plane, albeit is big, we expect the effects of this plane to be less and less. Do you guys understand that? So the distance y matters now. Expected, no? Yes? If you are close from the charge, you expect the effect to be strong. If you are far away from it, you expect the effect to be basically almost nothing, okay? So that is expectancy. Also, I'm going to use the arguments of symmetry and say that the electric field must be pointing away from it. So this is the direction of the electric field in here. The reason why, if you give me an argument that is this way or the other way, let's say, for example, you argue it's this way, since this is an infinite plane, I'm going to rotate it, okay, in such a way that this point in here spins with it. When I ask you, okay, look at the plane now. When you open your eyes, you tell me nothing has changed. The same charge Q, which is sigma Q over A, the sigma sprinkling of charges per unit area, is the same. So why in the board now the electric field is pointing in a different direction? So the only way to retain that symmetry is if the electric field is pointing this way. So if it was pointing this way, rotate it whichever way you want, it's going to stay rotating, pointing in that direction, okay? So that's one thing. If you tell me, again, I'm going to go throughout this entire distance y from the plane, as long as I am in the same distance y from the plane, I'm going to have the same magnitude of the electric field produced by this plane, as long as I'm at the same distance. You say, no, actually, I think, okay, I can tell you that the electric field in this point is less. If this is big, this is less, okay? Tell you, close your eyes, wait a second. I move the entire plane. Okay, if I move the entire plane, I expect this point to be shifted in here, and this point, of course, goes away. And now what was this much strength is less. I ask you, do you think the plane has changed? You say, no, it's an infinite plane. It still has the same charge distribution, sigma q over a, which is the same coulomb per square meter. So it looks like my plane has changed, but the value for some reason has changed. Okay, so in this case, I tell you, therefore, this value that you thought is this much is actually this much, because when I shift this one up or down, whether you're looking or not looking, it's going to retain the value. So by symmetry, I made the case for the direction and the fact that the electric field is uniform throughout a surface I can choose in here. So what I'm going to do in here, I'm going to take a Gaussian surface of area. Doesn't matter what the area shape is. So I'm going to take it of an area. I'm going to call it A prime because I just called the other one A. Okay, at a distance y from my surface, and by symmetry, actually I'm going to extend this one to the other side of the surface. Okay, because I need this one, I cannot end it really on the metal, so I need to extend it somehow, and I need to retain this symmetry. So for me to retain the symmetry, I really have to go a distance. If you call it this one y, this one actually is a distance y from the other side. Okay, and this area is the same as my other area A prime. Okay, hopefully you guys saw the symmetry. So this is like a rectangular shape, basically, of length 2y of an area, arbitrary area A prime. So A prime is a made up parameter. It's not part of the solution. So I better end up with no A prime in my solution. If I do have an area in here of the Gaussian surface, I have a problem. Now, I argued the electric field is pointing this way, so the contribution of the lateral surface now is going to be 0 because the electric field is pointing this way. This lateral surface is pointing this way, so the dot product of the lateral surface, this one, is 0. And so is this one, and so is the one in the bottom, and so on in the one on the other side. So the contribution actually from this problem is going to come from the basis. Now, the electric field is pointing in this direction, and the area A prime is pointing in this direction. So again, the dot product is going to give me positive value. Cosine of 0 is 1. The same thing in here. The area actually A prime is going put this way, and the electric field on the other side expected to be pointing in the other direction. But because I'm in the same distance, I expect the value also to depend on that distance. So the value of E and E are the same by symmetry. So these two areas, A prime and A prime, are equal in magnitude, and E are equal in magnitude by symmetry. And the angle between E and A prime is 0 on this side. And the same thing, the angle between this area and the electric field is 0. So there will be 2 times contribution from both areas. So the bases now are going to give me this value. They're going to give me, first of all, the lateral surface is going to be big fat 0 plus 2 times each one contribution. So it's going to be E, since it's uniform, is going to come out of the integral. And all I'm left with is E times the area A prime. So it's going to be E A prime. And the electric, the charge enclosed is this much charge only. And this area is exactly equal to A prime too. So this area is A prime, and I have sigma charge per unit area. So I have sigma times A prime of charge divided by epsilon naught. And that's good, because then A prime and A prime cancel, and we are in business again, because that's not good to have the made up shape contribute. And at the end, the electric field produced by this area, E, is going to be sigma over 2 epsilon naught. And we have what we need. First of all, the electric field does not depend on the Gaussian surface as expected, because A prime is the made up shape from the Gaussian surface. But something we didn't really expect. We thought the electric field will depend on basically how far you are, but it doesn't. So we need to think why that is, okay? And the reason why it's not coming into play, because if I move further and further, and if I take the element, for example, of the surface dA and start summing up, this part in here such to add up. So even if I move further from this point, the further points will contribute and compensate for the decreased values because there will be more contributions from the other end. So that is in a nutshell the explanation why actually this doesn't depend on the distance. It is constant. That is actually something that is strange, okay? It doesn't depend on this thing. So the biggest deal in here, this is a constant. You know how it is that when you write something in all caps, sounds like you're screaming? That's what I'm trying to say in here. I'm trying to scream out that this is actually a constant value. It does not depend on how far you are from the middle and that, from the surface. I'm sorry, this is an infinite surface. And as I said, it doesn't matter really what it's made up of. Okay, infinite plane. Okay, as long as it's plane, the electric field on both sides is going to be sigma over epsilon. Obviously, if sigma is positive, as I assumed in here, the electric field will point away from it. If the sigma is negative, the electric field is going to point inward of it. This result is very, very useful for capacitors. We will need them down the road for the capacitors. Okay, so this is not the capacitor yet, but it's needed for capacitors. Okay, for right now, just remember the contribution of the electric. If we did not really have Gauss's law, there is a very, very long calculation in here to get to this result with the integrals. As a matter of fact, even for the sphere, you really have to do a lot of integration to come up with those results. Gauss's law makes all of this somewhat easy. The only thing is you have to pay attention to the symmetry. What's going on? You make your case for the direction. If you move this way, that way, what happened to the direction? If you move here and there, what happened to the magnitude? Once you go through that trouble, then it's a matter of algebra in this case, because E comes out of the integral. And now just looking at the shape and identifying its area, multiply the two like I did in here. Area times E. The only reason I have the 2 because I have two sides contributing to this value. And then on the other side, then take advantage of the fact that sigma is uniform. That means the distribution of charge is uniform. And again, you end up with the same area or the same volume or whatever you're doing, the same line. So we did the infinite rod, which is a really linear problem. We did the sphere, which is actually a three-dimensional object. And now we did this two-dimensional object. The symbols used so far are lambda for linear, which has the units of Coulomb per meter. We use also sigma right now, which has the charge per square meter. And we used rho in the previous one, which has the charge per cubic meter. Okay, so that is basically the symbols we've used so far, and all of them you're taking advantage of the symmetry in the problem using Gauss's law. So Gauss's law is a very, very useful law actually, and it helps us solve a lot of problems. So let's see if we can do some of these problems now. Any questions before I delve into these things? No? Obviously, I'm not seeing the discussion, so if you're, I mean the comments, if you're making anything in there, so you need to speak up. Okay, so as promised, we're going to start with problem 52 because that's problem that sometimes they test on, so you guys need to understand how to do these problems. Problem 52 from the 15th edition. So it's problem 52. And on the 15th, if you have difficulty finding these problems in your 14th edition, please let me know, okay? Problem 52, and that is page 744. Okay? So again, the second item of the discussion is that you guys need to finish the calculations, because probably I'm not going to be able to finish this calculations, but just to get you going on it so that you understand what's going on. So this problem in here, we have a non-uniform. You know how I was saying all along, uniform, uniform, uniform? So we need to deal with something that is not a uniform distribution of charge, and this is one of them. Okay? So this is a non-uniform. that means rho is not constant. Or if it's lambda, it's not constant. Or if it's sigma, it's not constant. That's what non-uniform means. It's variable, it changes, okay? If it's uniform, that's a key word when you're solving problems or you're given an exam problem or test problem or homework problem, to look for these key words, okay? If it's uniform, you know these values are constant, okay? So you can start working with the problem. If it's non-uniform, then you're supposed to find it, or it's given to you, or you have to find a way of solving this problem with the non-uniform. So don't make an assumption that is not there, okay? So the first word, this is a non-uniform, but spherically symmetric. So we have symmetry, good, okay? We have spherical symmetry. Distribution of charge has a density. So they gave us the value on the sphere, how it looks like. They tell us that rho is given by this function, basically, that it is rho naught times 1 minus 4r over 3r, when r is less than but equal to big R, okay? And it's equal to 0, actually, when r is greater than or equal to r, okay? So this value in here, if I plug in r equals to r, it's not a continuous function at 0, but somehow it drops to 0 when we reach the edge, okay? Because rho, if I plug r equals to 0, I mean big R, this will become just 1, and I have 1 minus 4/3, and 1 minus 4/3 is some negative value in there, but somehow it drops to 0. So if I were to draw this function, it's for r equals to 0, it's rho naught, and then it starts diminishing. So it's a linear dependency, really. So this is how this function look like for the charge only. So this is r over r. I can draw it as a function of r over r, how far we are. So when we reach the edge, it's 1. So this is the limit of the boundary. When we are at r over r equals to 0, this is 1 times rho naught, okay? And then it starts to drop. At some point, it's equal to 0. When is it equal to 0? It's 1 minus 4 over 3r over r is equal to 0. That is equal to what? R over r is equal to 3/4, okay? So 3/4 of the way, the charge cancel, 0.75. So it's going to come out negative like this one. Then after that, it becomes 0. So there is a jump in here. So the function is not continuous in here. So this is the charge, basically. It starts from rho naught, and then becomes 0. And then right in here, it's going to be equal to 1 minus 4/3 is 1 minus, 3 minus. So it's going to be negative rho naught over 3, okay? So that's basically how the function changes with rho, okay? So you have to have that visualization, okay? You have to have how this charge is distributed. For example, if you look at problem 61, there is a complete different distribution whatsoever, okay? As a matter of fact, it's defined in 3 regions between r equals to 0 and r equal to big R. If you look at problem 47, there is a different distribution, and all of them are non-uniform, by the way, okay? So the limits are the sky, really, when it comes to this kind of problems, because you can think of any function in here for rho, and as long as you can integrate, you should be able to do these problems, okay? So this is basically the key thing as far as this one in here. But it's still symmetrical, although it's non-uniform, but there is a spherical symmetry in this problem, okay? So where rho naught is constant. So this number is constant. That's good, because if this is not constant, we have complicated function as a distance, okay? Find the total charge contained in the charge distribution. Okay, so first thing is we need to find how much charge is inside in terms of rho naught and r and all of that. So here is the sphere that we're talking about. Let's draw charge in here, okay? So it's positive, a lot of positive charge in the middle, which is rho naught, okay? And as you move around, it starts to become less and less, okay, from the distance, until at some point it vanishes completely when you are 3/4 of the way, So there is no charge at 3/4 of the way from the center of the sphere, and then it starts to appear again in a different sign, okay? Until we reach the edge, which is a bigger value, but it's a negative value, negative basically 1/3 of the rho naught in there, okay? And then all of a sudden it disappears. So that is your sphere, how it looks like. Where the blue in here, I'm trying to represent the positive charge, and the red in here, I'm trying to represent the negative charge. And that is basically how this thing is. Please do not read into it any politics, okay? No politics. I just occurred to my mind, politics. Don't read my thinking about politics about these colors, okay? Next time I'm going to draw it the other way around if you think that this is offending or you're somehow happy with these things, okay? Anyway, let's stick with the problem. Okay, we're doing physics, we don't care about politics. Politics is bad anyway. Find the total charge enclosed. So the total charge enclosed, I'm going to take a dV volume in here. And this dV volume has a charge dQ is equal to rho dV, okay? The only thing in here, I have to know what is the volume of, the element of volume in this case, okay? If I use this volume, it's going to be complicated because it's going to involve sine theta and sine phi and, I mean, cosine. Yeah, it's going to involve sine theta, d theta for this angle, and it's going to involve d phi from the other angle, and it's complicated. Instead, I'm going to take a sphere, actually, as my distance. I'm going to go an element dr away from it. So this is the element of volume that I'm taking. So think about it this way. Basically, you take a sphere of radius pr squared, 4 pi r squared. So that is the area of the sphere. So if I take this sphere now, this is how it looks like. Okay? And take a strip of it. So this is how it looks like. Basically, the base in here, that is actually, how should I try it? I'm trying to make a case for it. This is dr, okay? This height in here is dr. But the entire sphere in here is the area, not the length, okay? The area of the sphere is 4 pi r squared. So it's going to be 4 pi dr, okay? If you're not too happy with this explanation, all you have to do is just use polar coordinates, which gives me what is it? R squared dr sine theta d theta d phi, and integrate for the solid angle, okay? But this is basically taking the area of the sphere and times dr. If you wish, another way of looking at this expression, this is the volume of the entire sphere, and take dv from this expression, the r cubed cancel the r cubed, so you'll be left with 4 pi r squared dr, okay? So whichever way you convince yourself, this is the element of volume in this case, okay? So if we do that, then dq is rho times 4 pi r squared dr. If I plug this expression into my integral, the integration will become from 0 to big R of this term, of this function. So the charge enclosed then is the sum throughout the entire sphere of radius r, big R, of dq, which is equal to the integral from 0 to big R, because I'm doing the calculation through the R. So in other words, take the R equal to 0 and expand all the way to big R. So it's going to be rho naught times 1 minus 4 over 3 R over big R times 4 pi r squared dr. 4 pi and rho naught, they come out of the integral. And then we'll be left with this unique integral. And please pay attention to the next step because it's common for all of these problems. So Q, so this point in here, this is textbook method. This is what you do for this symmetrical problems that have this spherical symmetry. That's why I'm not including theta and phi in the calculation if I do a polar coordinates. If not, then that would be the case. If there is no symmetry, then the problem would be very hard to do, okay? So For all of these problems, this is what you plug in this expression, okay, for dv. So now, what we're going to do is we're going to take 4 pi rho naught, which is constant, out of the integral, and then we'll be left with the integral from 0 to r times 1 minus 4 over 3 r over big R times r squared dr. It is common practice at this point to make the following change of variable from the radius r to the dimensionless unit, which I'm going to call u, equals to r over r. Okay? If I do that, then this integration will become over dimensionless unit that changes from 0 to 1. So the boundaries of integration will go from 0 to 1, because when r is equal to big R, this number is equal to 1. That's one thing. The other thing from this expression is dr is equal to ru, whereas r is equal to ru. Okay, so that's basically rdu, I'm sorry. Okay, drdu, and then this is r is equal to ru. Okay, so now if I plug this expression in here, r over r, that is exactly u, and r squared will become r squared u squared, and dr will become another r times du, and now all of a sudden I will pick up an r squared from here, big R squared, and I will pick up another r in here, so it's going to involve an r cubed outside. So if I do the substitution and I'm careful with my calculation, this integral is equal to 4 pi r cubed, because it's not part of the, it's constants, it comes out of the integral. The boundaries of integration in this case are from 0 to 1 of 1 minus 4 over 3 u times u squared du. Okay, obviously this is just a polynomial, basically integral of the simple stuff, so I'm going to multiply u squared and integrate that part, and I'm going to have a u cubed. When I integrate, it's going to be u to the power 4, okay, divided by 4. So the integral again is going to be 4 pi r cubed rho naught, and I'm integrating from 0 to 1 of u squared minus 4 over 3 u cubed du. This integral is going to give me 1/3 of u cubed. This integral is going to give me, first of all, 4 over 3, 1/4 of u to the power 4. The 4 and the 4 cancel. Okay, and this is something to look for this type of problem. Sometimes they put these parameters there in the problem for simplification. You will see them canceling out, okay? But if they don't, you have to, they don't necessarily do, but sometimes that is the usefulness of these numbers in there. Anyway, let's plug in the boundaries of integration from 0 to 1. So this is a number. At the end is going to be number, because we took care of all of the r's outside. All of the constants are going to be outside. So this is going to be 1 over 3 times 1 cubed minus 0 minus what is it? 1 to the power 4 over 3, and this is going to be equal to 1/3 minus 1/3, and the whole thing is 0. So Q enclosed is exactly 0. Okay, and that is basically how much charge is enclosed. So how much electric field is outside? I don't know if the question is asked or not, but we know the answer to it. So if you're asked the question, since you found the electric field to be 0, because this has a positive charge and negative charge, okay? Albeit this one is less. Remember, it's negative 1/3. This one is a lot, okay? But the fact that this one is spread throughout a bigger area, albeit it's less per unit volume, but it's spread throughout a bigger area, so there is more contribution to it, and that seems what's going on in this case. They cancel each other. So at the end, this one has more charge, rho naught, in the center, and this one has 1/3 of a negative charge on the same charge on the other side, but somehow they cancel each other because of the fact that one of them is spread throughout a bigger area than the other one. So at the end, that's what we saw. We saw cancellation, perfect cancellation, and that's what the 4 was actually apparently for in this case. Okay, so Q is 0. So Q enclosed is 0. So if somebody asks you what's the electric field outside, the electric field outside is going to be 0. Why? Because if I take any Gaussian surface in here and wonder what is E dA over that Gaussian surface, this must be the charge enclosed, which is just found to be 0. divided by epsilon naught. So E outside is exactly 0. Okay. So I don't know if this question was asked or not, but this is something to look for. It's not always true that the electric the charge enclosed is going to be 0, but if it is, in these typical problems, that's how you do this. Is this clear so far, what I have done in here in the calculation? So far, it doesn't require from me. All you have to do is just follow the analysis that I have done and argue the case for it. Does it make sense to you guys?
Yeah, it makes sense.
Okay, so let's continue with the questions of this problem. Obtain an expression for the electric field in the region. Now, the second part. R greater than R, greater than or equal R. We already did it. So the next part in here, for R greater than R, for R greater than or equal to R, E is equal to 0. I just make the case for it because Q enclosed is 0. That answers that question. And so that's part B, by the way. Part C now, for the region less than or equal to R. Now that's going to depend on the electric, on the charge enclosed. So for that, it's the same calculation, except the boundaries of integration will go from 0 to little r. Okay? And so basically, we're trying to find an indefinite integral in this case, okay? But we start from 0. So it's the same value from here, from this integral. It's u cubed over 3 minus u 4 to the power 3. And the lower limit is going to be 0, whereas the upper limit is going to be u itself, okay? So we already did the calculation. There is no need to repeat it, but the boundaries of integration actually for q enclosed are going to be equal to, in this case, what did we use the units in here? 4 pi r cubed, 4 pi r cubed times rho naught times the integral from 0 to r, okay, of the 1 minus 4 r over, I'm going to change it to a dummy variable so that we don't confuse it to r, so that we're not tempted to put something in here. R prime squared dr prime, okay? Can always make that change a variable. And then, because the integrand in this case is just summing through a variable, at the end, the upper limit and the lower limit what matter in this integral. So again, if we make u prime equals, or u equals to r prime over r and do the integration, we're going to get into the same expression, except u now is evaluated at the value of r. So we're going to plug in the value in there, and this is the answer how it looks like now. Q enclosed is going to be 4 pi r cubed times rho naught times u cubed over 3. So it's 1/3 of r over r cubed minus 1/3 again of u to the power 4, 1/3 of r over r to the power 4th. Okay, the 1/3 and the 1/3 comes in here. R over r cubed, there is a cancellation of this r cubed with this r cubed, and then r cubed will come out of the integral. And there will be an r over r in here. So what I'm taking in here, I'm taking 1/3 of r over r cubed as a common factor in here, which is 1/3 of r cubed over r cubed. And this r cubed will cancel that r cubed. And the r cubed will come out of the integral, but there is one term that is left in here, okay? So there is to the power 4 in there. So this is how this expression look like. Q enclosed then, after you do the simplification, 4/3 of a pi of rho naught, because the r cubed is cancelled, times r cubed times 1 minus r over r, because that stays inside. It is always good to remember your dimensions, okay? This is, the charge has units of a charge, which is coulomb. This one, coulomb per square meter, per cubic meter, I'm sorry, the unit charge. The charge distribution is coulombs per cubic meter, and you have a cubic meter to cancel that, so this is a coulomb. And this one is a meter of a meter, so it has no units. So it's very important that you always have that first lesson actually in physics, where you do the dimensional analysis to play, and that you did, I think, in physics 4A. Okay, So we have the charge enclosed. We're going to use the Gaussian surface as being also a sphere. We're going to make the argument that this electric field is radial also inside the sphere. So we're taking this shape now. Let me go back into the problem. And I'm not going to repeat what we did earlier. From now on, basically, I assume that you guys know how to handle that. So inside the sphere, we are somewhere inside the sphere. So we're going to make the case of the symmetry, saying that this electric field is radial in the radial direction and the area is radial. And the dot product of the two is just going to be simply the product of their magnitude. Furthermore, it's the same value on the sphere because I can rotate, and they tell me specifically it has a spherical symmetry, so I can rotate the sphere whichever way I do. You wouldn't notice that the sphere has changed in shape. So again, the electric field magnitude stays the same. So I'm going to pull it out of the integral. All I'm left with is the area of the sphere, which I know is 4 pi r squared. So on the left-hand side of Gauss's law, what we have actually, we have the electric field times the area of a sphere, which is 4 pi r squared, and this must be equal to the charge enclosed divided by epsilon naught. So 4 pi over 3 epsilon naught times rho naught times r cubed times 1 minus r over r. And again, the r squared and this one cancels, so I'm left with the power of 1 in here, and this one cancels that one, and the electric field inside is not 0. Inside is some power law, so it's equal to rho naught over 3 epsilon naught times r times 1 minus r over r. Okay, so this is the function that I'm looking at for the electric field as a function of r. Okay, did I miss a term in here? Check the units again. It has to be a coulomb over distance squared and epsilon naught in the numerator. I have coulomb over cubic meter, and I have a meter squared, that meter that cancels that, and I will be left with 1 over meter squared, exactly what I need in here. Okay, epsilon naught is true for the electric field in this case. So this is the electric field inside the sphere. Okay, graph the electric field magnitude E as a function of R. Rather than do it as a function of R, I'm going to plug it as a function of R over R. So E as a function of R, I'm going to write it as rho naught over 3 epsilon naught times R over R minus R squared over R squared. Okay, it's much easier to do it this way and deal back with my unit U again, which is R over R. So I'm going to plug it as a function of that. So this is the function I'm trying to plot, U minus U squared. Everything else is constant in here, which I can throw under the this one and call it E naught. Okay, so for U equals to 0, E is equal to 0. For U equals to 1, namely when R is equal to R, where U is equal to 0, U is equal to 1, I'm sorry, then in this case also it's 0, E is equal to 0. So the electric field starts from 0, ends up in 0, and as a matter of fact, outside of the sphere is also 0. We just argued that. So it starts from 0 and ends up back into 0 inside the sphere. So we start with no electric field inside, and right at 1, this is R over R, by the way, the electric field, which I'm going to draw it as a function E divided by rho naught R, and then I have 3 epsilon naught. So the electric field in terms of this E naught, if you like. So this would be my E naught. Okay, so this is, it's going to start from 0 and end up back into 0 somehow. Okay, so that is the electric field in here. Now, how is this function depending? Okay, I know the derivative of this function with respect to U vanishes at a maximum or a minimum. So what I do in this case is going to have to take the derivative with respect to U instead of with respect to R. So it's going to be 1 minus 2U equals to 0. This is 1 dE over du equals to 0. Okay, took the derivative in here quickly because the other parameters in here are just constant, so I'm left with this dependency with respect to R. So U minus 1 minus 2U equals to 0. That means that U is equal to 1/2, or R is equal to big R over 2. So midway somewhere, the electric field is either a maximum or a minimum. How do I know if it's a maximum or minimum? First of all, I can check its value. At that point, I will have 1 minus 1/2 squared, which is 1/4. So it's going to be 3/4 of E naught. Okay, so and it's a positive value in this case. Okay, so that is how this one is. Actually, it's a parabola. So if this were E naught, this is actually 3/4 of E naught. Okay, so that is basically the value when it's maximum. As a matter of fact, I can check if it's a maximum or no by taking just the second derivative. The second derivative of 1 is 0. The second derivative of -2u is just -2. And that is a negative value. That is, again, a check that this is actually a maximum. And that is basically how the behavior of the electric field is a function of how far we are. So it starts 0. The electric field starts 0 inside the sphere and starts to grow until it reaches its maximum value, which is basically 3/4 times this value that I drew earlier, E naught. And E naught is 3/4. So basically it's going to be rho naught R over 4 epsilon naught. That is the maximum value. And then it starts to diminish again until I reach the edge where it's going to become 0 and stays 0 thereafter, because outside it's 0. So this is how the electric field depends on how far we are from the center of the sphere. So, and then it's going to stay 0 everywhere. So this is how the electric field looks like. Okay. And then what's the other question? It doesn't look like we're going to get to another problem, but at least we got this one done. Find the value of R at which the electric field is maximum, and I just did that. Okay. That is actually half R over 2. Here is the challenge. I want you really to be at ease with this kind of problems, because as I said, problem 61 and problem 47, which I think they might be part of the homework anyway, you're supposed to understand thoroughly how to do these problems. Any questions about this kind of problems? I know I did it in a lot of detail, more than I actually was thinking to do, but it's fine. Any questions about this problem? No? Does it make sense to you guys, at least the whole analysis from the beginning to the end, with the rope not being uniform? Yes? Maybe? No?
Yeah, I think so.
Okay, thank you. Okay, everybody, it will not make sense to you and you will not be at ease with it unless you actually do it yourself, okay? Because watching me doing it is not going to be helpful to you, okay? So what is the takeaway? Thank you very much, Harris. Let me explain what is the main points in here of these typical problems. These typical problems, first of all, try to identify the symmetry. Of course, in this case, it's spherical symmetry. In other problems, you may not have spherical symmetry. It's probably cylindrical symmetry and things like that. And that dictates what kind of shapes you're going to be dealing with. Now, for a spherical symmetry like this problem, this is key for DV. Okay, so when you're dealing with DV, when a spherical symmetry is spherical symmetry only. So if it's cylindrical symmetry, you're going to have a different problem to deal with. Okay, if you're dealing with cables, for example, things like that, that's cylindrical. This is a key thing for DV. Do not forget this expression for DV. Okay, that you will need. The fact that it's non-uniform, you're going to be summing through the volume. So you need that value. Okay. Although I told you guys in the beginning that the trick of Gauss's law is to really not do as much integral as possible. This is the case where you have to do some integrals. Okay, you have to integrate some. If it's uniform, then there is no integration whatsoever. It's non-uniform, that is when you actually have to integrate. And as you saw, these integrals are just polynomials. These are simple integrals of u squared and u cubed in here, which turn out to be u to the power 3 and u to the power 4. This is basic stuff that you guys must have learned somewhere in your calc classes up to this point, okay? We didn't do a triple integral. We didn't do a double integral. As a matter of fact, for the other side of Gauss's law, I did not even write the integral form. I already wrote the answer, namely, where is the Gauss's law? This one. So this is the other side, basically, of Gauss's law because of the symmetry. Again, I argued the symmetry one way or the other. The fact that there is spherical symmetry, the electric field is pointing upward. So E and the area are pointing the same thing. So the dot product becomes just simply the regular product, basically, of the two magnitudes, because cosine of 0 is 1. And then I also argue the fact that the electric field has to be uniform throughout the entire sphere because of the fact I have spherical symmetry. So now E comes out of the integral, and I'm left with is the area of a sphere, which is 4 pi r squared. Okay. So that is basically how we applied Gauss's law. So this is the key in here. This is where Gauss's law came into play. Okay. And then after that, we finish the calculation, which is pure algebra at this point, and a little bit of a graphing thing, which if you're in doubt, just graph this function as a function of r over r on a calculator, basically, or graphing device, and you should be able to find this very same shape. Don't forget that E is 0 outside of the sphere. That because of the fact that Q is enclosed is 0. Okay, since Q enclosed is 0, so the electric field outside. And this is a confirmation, basically, when you're doing discussions, this is confirmation that the electric field is continuous at this point, okay? Basically, it has 0 and stays 0 throughout, okay? That's what confirms it. The electric charge, there is no problem with it being the way it was in there, because you physically, basically, this is an insulator, so you purposely, you take charges from this end and push them in here. But if you do that, then the distribution becomes imbalanced because now they're thrown throughout a bigger area than they are condensed in the middle. Okay, so the ions in here will have bigger charges than this side. So if you sum up the charges again, you have no charges because you took from this guy, you borrowed and you gave to the other one. At the end, you have no charges. And that's exactly what this thing is. What the math is telling you. Q enclosed is 0. Okay, so which means that the insulator that you start with stays the same. Outside has no charges enclosed, so there is no electric field outside. Okay, so all that is going on is inside because of the way you redistributed the charges inside the insulator in this case. So definitely you have electric field, and that electric field is exactly this shape. Okay, outside is 0, inside it has this curve in here. Now, if you look at problem 621, it's not going to have probably this smooth shape, but at the end, you should look for the signs of continuity and things that I was talking about, okay? Problem 47 also may not have the same shape, as a matter of fact, for the electric field. It may be finite value outside because rho inside is not exactly 0, okay? I mean, Q inside is not exactly 0. So the fact that I have 0 in here is because of the fact that Q was in 0. If it was not, then this problem would be different, okay? So this is basically in a nutshell. So here is the deal. I want you guys to go back through these very same steps that I did. That's the other item. I want you to go through this very same steps that I did in here for this problem and understand them. And if you have any questions, please let me know so that we clarify them. Come back to this video if you want to, and make sure that it's at ease with you and you understand how to do this problem. And then try on your own, if it's not already assigned part of the homework, problems 47 and 61, and let's see if there is more problems like that one. Actually, problem 45 also looks like it, okay? Okay, so try those things in there because you will be tested on stuff like this one. As a matter of fact, if you're not tested right now, again on this exam, you will be tested in time when we do the magnetic field, because the magnetic field has to do with the distribution of the currents. Is this better now, Harris? That is the explanation. I know that you need to go through it. Okay, everybody else, please, okay, I need you to really be spending your time on this stuff, reading through them, going through the examples I do, and also doing the homework. And if you do have problems, please let me know. Rami, were you trying to say something?
Yes, Professor. Hey, real quick for you, it's kind of a little bit off topic. It's about the lab, actually. So for the lab, do we just to clear things up, do we just fill it in on the computer, or do we print it out and then like write in the answers? Or is it option, like how does it?
Better is easy for you. Again, the form is not a required one, so if you can fill it out, that's easier actually.
Yeah, okay.
For you and for me, because you can read it. But if you have difficulty with it and you'd rather write things down, you can do it, but make sure when you take a picture or you upload it back, you can read it, okay?
Yes, sir.
So
Oh, adding on to that, to his question, Professor, if we do say take a digital version of it and edit it, did you want it back as a PDF or does it like matter at all?
Ideally, as PDF is better. That guarantees that your work is the same everywhere. But if you write it in Word and you're using this beautiful, nice font that you have in there, and probably I don't have it, so what happened in this case, your work will look kind of a language that I don't know what it is, so I wouldn't be able to do it as would. So it's a good idea to convert it back to a PDF to retain the format, okay?
I understand.
Okay, no problem. Okay, I will see you guys on Wednesday. As promised, we still have at least 2 more problems. I'll try not to go in as much depth as we did today with this problem. And we will go through the discussions later on, and probably we'll have the lab still, at least to get more in-depth practice and talk about homework stuff and things like this. It sounds good?
Yes.
Sounds good.
Yes, sir.
Okay, so let me stop the recording, and I will see you Wednesday.
Oh, Professor, quick question.
Yes.
Can I talk to you in private after class real quick?
Sure, and we'll do it without recording, okay?
Okay.
Okay, everybody else, you can see you Wednesday. Thank you.
Zebra.